as I said in the last video, this video contains the calculations for the independent samples t-test. There's a few extra calculations that we need to make because we're now dealing with two different samples. And so it's a little bit more complex, but I don't want this to put you off. You've got this. We can take it one step at a time. Let's take a look. So in this video, I'm going to talk with you about the notation that we use in the independent samples t-test. But most importantly, I'm going to talk to you about that denominator formula. We have been using standard error in our denominators for our one sample t-test and our z-test, but now we have to use something called pooled variance because we don't just have one sample, we have two. All right, we have two samples, which means that we're going to have to really identify what is sample one and what is sample two. So this is what your notation is going to look like. So for the null hypothesis, for example, you see the population mean of sample 1 minus the population mean of sample 2. And the alternative hypothesis, the population mean of sample 1 minus the population mean of sample 2. And as a reminder, we might have two samples in front of us, but our hypothesis is really about the population from which they came. So when we're talking about the means of the samples that we have in front of us, we're going to use a capital M. But this time we're going to have subscripts 1 and 2 to identify which is the mean of group 1 and which is the mean of group 2. And then finally, when we're talking about the sample, the n, the number in the sample, we're talking about the sample number for group 1 and the number for group 2. This might seem really elementary, but it can be a little bit tricky with all these different subscripts. So just keep in mind that they help us to figure out which group we're talking about. Here is the T formula. Wow, there it is. So basically we have a couple different elements. I'm going to start with this element here, which is the mu of 1 minus the mu of 2, or the population mean of 1 minus the population mean of 2. This comes from the null hypothesis, which means 0. Our null hypothesis is going to state that there is no difference between our two groups. They are the same. So this in parentheses is always going to be equal to 0. And in fact, we're not even going to use this part in parentheses. It's here for a formality right now. But the null hypothesis is always 0, so we really don't even need it. Anything minus 0 will be that original number. So for our t statistic, we're going to take the mean of the first group. We're going to subtract the mean of the second group. And then we have a standard error, a new different way of looking at it. And our standard error comes from the data. It's going to represent the difference between both samples that might be reasonably expected. So this is sort of what you would expect to see basically, and this is what you are expecting to see in our samples. We'll talk more about that. So again, when we have our T formula, I'm just going to wipe out that second part because that's always going to be equal to 0. So basically our T formula is going to be mean of 1 minus mean of 2 divided by our standard error. So how do we measure standard error? Well, it's going to reflect, as I said before, the difference about how much is reasonable to expect between a sample statistic and the population parameter. So each sample mean represents its own population mean, as we've said before. But in doing this, we now have two sources of error. In a one sample t-test, we only had one source of error, and that was with our one sample. But now we have two sources of error. So the mean of 1, the first group, approximates the population mean, but it has some error. Remember, when we draw a sample, there's always going to be some sort of error. I mean, we might freakishly draw the exact same sample, but not very likely. There's always some error. And the mean of the second group approximates its population, but again with some error. So instead of just having one sample with its own error, we now have two samples with their own particular error, and we have to find a way to put that error together. So I'm just going to share with you the difference between the one sample t-test and the independent samples t-test. So the sample data is the mean in a single sample t statistic, but in independent measures, the sample data is going to be the difference between the two groups. That's the number we're going to be looking at is the difference between the two groups. The hypothesized population parameter is the mu for the single statistic, single sample. But for independent measures, it's the population mean for the first group minus the population mean of the second group. So that's just kind of getting us started. These last two pieces are the parts where we start to see something different, but actually we're only just doubling everything in a certain way. So for example, this was our estimated standard error for a one sample t-test. And if you will recall, it's the square root of variance over n, or it's the standard deviation over the square root of n. So there's two different ways of writing that. But what we're going to do with the independent measures t-statistic is we're just going to split this out and then come up with a standard error that reflects both groups. And then this is variance here, sample variance. And the way that we find sample variance when we have one sample is just the sums of squares divided by the degrees of freedom. Well, we don't have just one sample, we have two, so we have to combine that. And so our sample variance formula is going to be something called the pooled variance. And we're going to add the sums of squares for the group 1 plus the sums of squares for the group 2, put that together. We're going to add the degrees of freedom 1, degrees of freedom 2, and then divide. So we'll go over this step by step, don't worry about it. So again, we have two sources of variance. We have the variance for sample 1, we have the variance for sample 2. That gives us two sources of error, but we need to combine these sources of error. So we need to come up with something called the pooled variance. I mentioned that already. So even if at this point you're not understanding why we do this pooled variance or whatever, I want you to kind of think about the formula for pooled variance and how you get it. Just get the formula down and it will come. So this is the symbol for pooled variance right here. So it's the variance symbol with a little p, which means pooled. So basically we're taking the variance for both samples and we're putting them together. And we're doing that again by taking the sums of squares for group 1, the sums of squares for group 2, adding them up, then taking the degrees of freedom for both groups, adding them up, and then dividing, and we end up with a pooled variance. Okay, so we're going to give this a try. Two samples that are the same size with an n of 6. One sample has the sums of squares of 50, and the second sample has the sums of squares of 30. What is the pooled variance for this example? Well, let's work it out on the board. Okay, so what we have here is the formula for pooled variance. This is the symbol for variance, that P means pooled. To find the pooled variance for an independent samples t-test, we take the sums of squares for group 1 plus the sums of squares for group 2. We divide it by the degrees of freedom of group 1 plus the degrees of freedom for group 2. We already know the information that the sums of squares for group 1 is 50, the sums of squares for group 2 is 30. We don't have the degrees of freedom, we have the n for group 1 is 6, and the n of group 2 is also 6. So to define the degrees of freedom for each group, I'm just going to do n minus 1. So the degrees of freedom for each group is going to be 5, right? So let's plug everything into the formula to go ahead and find out the pooled variance. So the sums of squares for group 1 is 50, and the sums of squares for group 2 is 30. And I'm going to divide that by the degrees of freedom for group 1 plus the degrees of freedom for group 2. So we basically have 80 divided by 10. So our pooled variance in this case is going to be 8. Okay, once we find the pooled variance, we're not off scot-free because we need to find the estimated standard error. So we use variance and standard deviation to find the standard error in a one sample t-test. But now we have to use pooled variance to find the standard error to complete an independent samples t-test. So how do we do that? It's not hard. Again, you may not understand exactly why we're doing this at this point, but just get to know this formula. So our standard error formula, we call this the standard error of the mean difference between group 1 and group 2, is going to be thus. We're going to take the the pooled variance, divide it by the number in the first group. We're going to take the pooled variance, and divide it by the number in the second group. We're going to add these two things together and find the square root. So there's a couple different steps to that, and we will work that out as well. So here is another example that we'll try. We'll work it out on the board. Two samples that are the same size, n of 6. One sample has a sums of squares of 50, and the second sample has a sums of squares of 30. We've already figured out the pooled variance, but now we need to figure out the standard error. So what is the estimated error for this example? And why did I just say estimated error? That is because we are using a sample to estimate an error in the population. Okay, let's work this out on the board. Now that we have the pooled variance, we can figure out our standard error term, our standard error of the mean differences. So let's take a look and see what we have. Our pooled variance was 8. We already figured that out. And we have to remember that we had 6 in each group. That's going to be helpful to us. Here's the symbol for the error, for the standard error for this independent samples t-test. It's the standard error of the mean differences. And the way that we find this is we take the square root of all of this in the middle, which is the pooled variance divided by the n of the first group, plus the pooled variance divided by the n of the second group. So we can do this, right? So let's just start plugging in. So I'm going to just keep this square root. And for pooled variance, I'm going to put 8. And for n of group 1, I'm going to put 6 plus. And I just put the pooled variance again. And this time the n of group 2. Now the group sizes don't always have to be equal. In this case, they are. So let's do a quick division inside the square root formula first. So 6 goes into 8 1.33 times. 6 goes into 8 1.33 times. So we're basically looking for the square root of 2.66, which if you had your calculator, you could figure out is actually 1.63. So in this case, our standard error for this independent samples t-test is going to be 1.63. Okay, so that is going to be all the convoluted calculations that we're going to do. We're going to do Cohen's d at the end, but this is basically it. So this is what you need to know this week in terms of how you need to find the standard error. Of course, we're going to plug that standard error into the t formula to be able to figure out what our t is for our test. And in the next video, I'm going to speak with you about degrees of freedom for the independent samples t-test.